Greetings to all the viewers. Now the session is going to deal with 1,3-dipolar cycloadhesion reaction. It is the part of organic named reactions. We already conducted series of sessions based on organic named reactions earlier. All are available at the channel called World of Conceptual and Competitive Chemistry. In addition, we already gone through heterocyclic compounds, natural products, reagents, so many alkaloids, terpenoids. So all these compounds are available. In addition, graduation chemistry, post-graduation, intermediate chemistry, 10th class chemistry, all these kinds of conceptual representation, academic perspective, research perspective, and also competitive examination purview, all are available at the channel World of Conceptual and Competitive Chemistry. Right. So the concept 1,3-dipolar cycloadhesion taken from the textbook authored by Dr. Kavitha Kotthireddy, Kota, textbook of organic named reactions. It's also known as Huesen cycloadhesion reaction. 1,3-dipolar cycloadhesion is alternatively named as Huesen cycloadhesion reaction. It is the kind of 3+2 cycloadhesion process. 1,3-dipole and a dipolarophile. 1,3-dipole and 1,3-dipolarophile are going to combine together 5-member ring, that is a heterocyclic compound formation taking place, right? So 1,3-dipole means for one positive and negative charge is called a dipole, and another is dipolarophile is taken in addition. So both are combining together and the 5-member ring formation mean for the heterocyclic ring formation is possible. General concept, it is the part of pericyclic reaction. Moreover, it is concerted in nature. Most of the pericyclic reaction pathway may not be isolated and understandable, rather, which is concerted in nature. Woodward-Hoffmann rules are the guidelines in order to run this Huesen cycloadhesion process. Mechanism where the highest occupied molecular orbital of one of the component dipole and the lume of another dipolarophile are reacting together. In accordance with the symmetry operation, symmetry conservation is taken over so that final product 5-member ring is possible. Here, outcome of this reaction will be 5-member ring formation. Moreover, heterocyclic ring will be established. Triazoles, isoxazoles could be the final products by means of this 1,3-dipolar cycloadhesion process. If you want to observe the entire process of reaction, 1,3-dipole was taken. So here this is the kind of 1,3-dipole. You can notice here the kind of azide molecule with the charged species over there, and here is the another molecule called alkyne or alkyne you may take. So I am taking alkyne, terminal alkyne was taken for the consideration. So these two molecules are supposed to be proceed for the cycloadhesion reaction, right? How could you achieve the cycloadhesion process? Here the triple bond and this azide molecule are taken part of this cycloadhesion reaction. Two provisions you noticed. With this triple bond you have this kind of phenoxy moiety that is located at the position of 4th carbon atom, and here the nitrogen directly linked with this benzyl functionality that is indicated at the position number 1. This is one possibility, or else here you may go for the reaction of this alkyne in the flipped manner. You can rotate this alkyne molecule, and this terminal carbon is going to react in an opposite direction, so that here the 5th carbon is accompanied with this phenoxy moiety. So both the provisions we have. If the direction is in this manner, that could be 3A product. If the direction in opposite manner, the 3B product you can achieve. So that mixture of products are possible. That depends upon the synchronization of the starting materials in order to achieve this triazole as the final product. If you want to observe this example pertaining with 1,3-dipolar cycloadhesion, I am taking azide and simply indicated with the terminal alkyne. Both are supposed to be treated together. So being 3 nitrogens are taking part of this reaction, so that triazole formation taking place. Anyway, this nitrogen is having this alkyl group that is located over the nitrogen as well, without any disturbance. And moreover, that in next carbon atom is having alkyl alkyl that remains again over there. This is one kind of product. If you are flipping the entire alkyne in opposite direction, there is a possibility you can notice the product will be in this dimension. So this is the way mixture of two products that depends upon the orientation of alkyne which going to react with this azide. So that's reason why mixture of two compounds or two triazoles we are achieving based on the synchronization of starting materials. So this is called alkyne and this is said to be alkyl azide. Triazole could be the final product. That alkyl substitution depends upon the orientation of alkyne. Common azides may be taken over there. So if you are taking azide, there could be triazole as the final product. Nitrile oxide if starting material, instead of 3 nitrogens, rather you are taking carbon nitrogen oxygen, there will be a product isoxazolines formation is consequence. And nitrile imine, if we are having triple bond N and single bond N, if taken, there is a provision for 2 nitrogens containing the ring system. So that is also the provision, that is a kind of pyrosol. Here the ozonide precursor if taken, selenium trioxide, they will proceed for the ozonolysis. So these many possibilities we have, these many product formations also we are able to accomplish by means of 1,3-dipolar cycloaddition process. If you want to observe the reaction mechanism between these two, how can we go for the reaction? That is indicated over there. I am taking dipole, that is a carbon, triple bond nitrogen and oxygen, that is said to be what? Nitrile oxide. This is called nitrile oxide. Nitrile oxide is a charge separated. Oxygen is accompanied by the negative charge, where nitrogen is possessing positive charge. This is called dipole, and dipolophile was taken as a triple bonded compound. Triple bond is alkyne moiety, alkyne functionality located over there. So here the oxygen negative charge taking part of the reaction between the carbon acetylenic carbon atom, and ultimately the triple bond, one of the pi bond is taking part of the sigma bonding between the carbon atom of alkyne to that dipole carbon atom. So this is the way bond delocalization taking place, and subsequent pi bond between the carbon to nitrogen is moving toward the nitrogen, being it is experiencing positive charge over there. This is the way 3 bonds delocalization simultaneous manner, being it is a concerted mechanism within the single step immediate delocalization taking place. How can we say this reaction is 1,3-dipolar cycloaddition? Among the first, second and third, first to third atom, the reaction is taking pi cycloaddition. This is the way 1,3-dipolar cycloaddition is the name indicated by Huesen. So Huesen is the eminent scientist who gave the idea of 1,3-dipolar cycloaddition process. Ultimately, here the notice of nitrogen oxygen containing 5-member ring, which is obviously denoted as a isoxazole. Isoxazole synthesis is accomplished by this 1,3-dipolar cycloaddition of this nitrile oxide with the acetylenic bond by 1,3-dipolar cycloaddition process. Here is another example pertaining with this 1,3-dipolar cycloaddition. You can notice the molecule with azide. 2 azides are reactive, and therefore the provision to react with the 2 acetylenic functional group. This is the dipole and this is another dipole. So here 2 active sites are located within the single starting material. That's the reason why this pyridine is also having 2 active sites once again. That's the reason why in both the dimensions you can extend this 1,3-dipolar cycloaddition process in the presence of copper or else copper diacetate catalyst. TBTA is taken, tetrabutyl tribromide taken as a kind of phase transfer catalyst. Tetrahydrofuran is a solvent media in addition to the methyl nitrile So it is also called as acetonitrile. The reaction taking place, our focus must be upon the functionalities active towards 1,3-dipolar cycloaddition. Here the azide is going to react with the triple bond over there. Whenever the reaction is accompanied, obviously there will be origination, there will be a establishment of a kind of triazole molecule. Triazole will be established over there, and another side also we have active azide functionality. Again you can go with this alkyl. Entire alkyl is going there, entire alkyl is going toward this side, so that here also you can establish the another triazole ring system. Anyway, pyridine is taken up by one of the triazole molecule, and being the process is endless and it is repeated continuously, being these are taken as monomers, so that here the polymerization process you can extend the chain as we are wishing to extend the number of possible 1,3-dipolar cycloadditions in the similar manner. Here is the possible mechanism indicated in the cyclic form. Let me show how the cyclic form is represented. Right, so in order to achieve this 1,3-dipolar, so in order to achieve this triazole molecule, this is triazole, right? So first of all, let me treat this first compound called acetylene. Acetylene could be the starting material for this reaction. That acetylene is going to react with the metallic copper. Copper metal is a facilitator for 1,3-dipolar cycloaddition reaction. So that acetylene is supposed to be treated with copper metal. So here the coordination bond between the pi electron cloud of this triple bond with this copper metal being d-orbital is vacant and having Lewis acidic nature to accept, and there will be a coordinate covalent bond formation between the acetylenic compound with the copper, so that complexation is arrived. After that complexation, let me go for the addition with another copper atom as well. So whenever one more copper atom is added, copper metal is added, being a triple bonded carbon is experiencing acidic hydrogen at its terminal. Acidic hydrogens are more provision to release the H positive, being carbon is more electronegative in nature, sp hybridized carbon. That's the reason why having strong affinity for the bonded electrons and the free liberation of H plus. So acetylenic protons are more acidic in nature. That's the reason I immediately replaced with one more copper metal. This is the way copper acetylide will be originated. Now this activated acetylenic compound is supposed to be treated with the alkyl azide. Azide is having the 3 nitrogens taken in the linear fashion. 3 nitrogens are taken in the linear fashion with the dipolar molecule. So this dipolar molecule is represented over there. Here the nitrogen to nitrogen bond is located. Here the nitrogen experiencing negative, and most probably there's a quaternary nitrogen with a positive charge. Whenever this molecule is in contact with this acetylene with a copper bounded one, copper catalyzed one, so immediately pi electrons having more affinity towards binding with this nitrogen atom, so that your electrons are running toward this side, and ultimately there is pi electrons between the two nitrogen atoms are moving toward the electrophilic nitrogen atom, and the electron reach another adjacent nitrogen atom will bind with the copper metal. This is the way 3 atoms and 4, 5, 6, a 6-membered ring will be originated. The 6-membered ring is indicated in this manner, where copper to nitrogen bond is indicated in the dotted line, being it is not that extent stable. That's the reason why dotted line bond is indicated, and another copper is also competing with that one. Not only one of the metallic copper, rather another copper is also there, right? So this acetylenic carbon is having another copper as well. That is also interfering with this bonding, so that nitrogen having slight extent a reaction with the one of the copper, and another extent a reaction with another copper atom as well. This is the way here the allocation of the bond, allocation of the new bonding is possible. So this ambiguity, the molecule is looking like somewhat complex, right? Immediately it will go for the release of one of the copper metal like this. So this is the copper which is released over there, so that the nitrogen now realized to bind up with this carbon atom rather than copper atom. That's the reason why 6-membered ring is now concised into 5-membered ring system by the release of one of the copper, and another copper again remained on this carbon atom, acetylenic carbon atom only. Moreover, you got the 3 nitrogens within the 5-membered ring system, which is called anyway this is said to be what, a triazole molecule only. But this is not the requisite final compound. Rather, we need to release another carbon atom from the system by the simple protonation process. Whenever you are adding with any kind of protonating agents, immediately they are able to replace this copper with this hydrogen atom. Ultimately, you are going to achieve the final product what you are expecting. That could be triazole molecule. This is the way 1,3 dipolar cycloaddition is accomplished. That 1,3 dipolar cycloaddition step exactly followed in this process. Here, this is a step 1,3 dipolar cycloaddition is accompanied. Entire mechanism is provided, and the regeneration of copper metal, that will again go for that activation of another molecule of acetylene, another triazole molecule formation taking place by Huesen cycloaddition process. This is the entire mechanism in a clear description manner. Let me give the examples related with this 1,3 dipolar cycloaddition. It is 1,3 dipolar cycloaddition is a successful organic named reaction with plenty of literature over there, plenty of reactions taken part of this mechanism. So that here you can notice the kind of terminal alkyne and going to treat it with this aromatic azide compound. So whenever this is the case, you are going to treat ultimately there is a establishment of a triazole molecule as a 5-member ring system, and here that nitrogen already had a benzyl functionality that remains on this nitrogen only. And this carbon atom, acetylenic carbon atom is having that alkyl functionality that again remains on that position number 4. This is the way triazole molecule formation is taken. In order to understand the reaction in the real manner, there is a provision for the interference of copper first. Copper is the catalyst used to facilitate the reaction, foster the reaction. So a hydrogen of this acetylenic bond is replaced with copper, being it is acidic in nature. After getting this 6-membered ring first originated, later on it will be concised into the 5-membered ring system with the 3 nitrogen atoms in the adjacent center, and this is called what? Triazole molecule. Now let me give the synchronized form of this cycloaddition process. 3 nitrogens taking in the linear fashion, and the acetylene is another reactant taken for the easy reaction annihilation process. In order to make this cyclization, there is a requirement of slight heating, raising the temperature, able to reshuffle the bonds. Existing bonds will be delocalized and new bonds will be originated. And there is a provision for either alkyl substitution at the position number 5 or else 4. This is the way 1,4 regioisomer or else 1,5 regioisomer will be originated by means of this 1,3 dipolar cycloaddition process. That depends upon this olefinic acetylenic compound arrangement. If you are taking this manner, 1,4. If you are taking flipped manner, 1,5 regioisomer, both the provisions are there so that you will get mixture of 2 products. Here is a kind of reaction in both the provisions, both the named reactions are taken over there. Azide is supposed to be treated with acetylene. In the process of using 1,3 dipolar cycloaddition, provision for the mixture of compounds rather than the single one. So both the possibilities we are having those. That's the reason why always this Huesen reaction is giving rise to mixture of 2 products, as we already aware about them. But the same reactants are taken with the copper acetyl acetate click reaction, so that is giving only single product. What is the selective product formation is possible. This is another provision. So both the named reactions are driven by same starting materials, but the mechanism will be different. Here azide supposed to be treated with alkyne under heat condition. There is a provision for either 1,4 or 1,5 isomers of triazole. You can achieve 1,5 substitution of alkyl group. Remaining skeleton of triazole will not be changed. Rather, only the position of this alkyl group will be varied. Azide treated with alkyne copper catalyst under water conditions. Here you can notice the provision for the product formation. First, second, third, fourth position we are having that alkyl group. So that fourth position is having alkyl group. And the same azide treated with this triple bonded compound. Here ruthenium catalyst was taken. Ruthenium catalyst, ruthenium chloro PPH3 catalyst was taken. At this condition, this entirely bounded to only one product, that is the fifth position alkyl group noticed. Copper catalyst imparting alkyl at the position number 4, whereas ruthenium catalyst is shifting that position of alkyl group to this position number 5. This is the way many factors are operated. They are taken into the picture in order to understand the mechanism for this 1,3 dipolar cycloaddition process. Now we entered into the segment of applications of 1,3 dipolar cycloaddition process. Click chemistry. Huesen 1,3 dipolar cycloaddition between the azide and alkynes are taken. So simply it is considered a mechanism within short span. There is a formation of product 1,2,3 triazole is the ultimate product. Widely used in the drug design, material science and bioconjugation as well, right? So in order to manufacture new drugs, materials of high impact, high applicability, so bioconjugation containing one also fabricated by this 1,3 dipolar cycloaddition process. Natural product synthesis like heterocyclics will be manufactured by this 1,3 dipolar cycloaddition. Green chemistry, high atom economy will be there. So whatever you are reacting, the extent of product formation is also maximum in the extent, and very mild conditions are sufficient in order to go for the extreme conditions like higher temperature conditions and harmful chemical usage. All those are not yet all taken into the consideration. Rather, the reaction is perfectly satisfying green chemistry protocols. So by this we successfully accomplished the entire 1,3 dipolar cycloaddition process, and it is the important application oriented named reaction in the synthetic organic chemistry and even natural product manufacturing. In the next session we will deal with the Dobner modification. Dobner modification will be the next session for the day. So here we concluded this 1,3 dipolar cycloaddition. Hopefully you got the informative lecture over there, and you can watch regularly, and so if you observe the entire session from starting to ending without any interruption, definitely this reaction will give the knowledgeable insight for your preparation, for your academics, research and also competitive examination. Follow the channel regularly. You can subscribe, watch regularly and share with your friends so that you will definitely get the success in your field. Thank you very much for your patient listening. Signing off, Dr. Kavitha, Kotthireddy, Kota.